Hi, my name is Andy Steve Lojuntin. I'm the group leader from group Numerical. For this group assignment, I have chosen the part B, which is about the third order Lagrange Interpolating Polynomial. So, what is third order? What is Lagrange Interpolating Polynomial? Well, basically, it's another method of curve fitting, just like Newton's polynomial, which with a little difference, which is that it is a reformulation of that same method that avoids the computation of divided differences. As you can see over here, this is the general form, and this one over here stands for this term over here. Okay, so how do we introduce this into our simulation? Let's go to the next slide. We introduce it in form of Neville's algorithm. What is Neville's algorithm? Basically, this algorithm shows you how to construct a coding for Lagrange Interpolating Polynomial. So I got this from MAT 772 lecture notes by Mr. Jim Lambers from University of Southern Mississippi, and since I'm using Matlab instead of Excel, this will be very useful. Sorry, it has been very useful since I already did it. Okay, so let's go to the snippet. So this is how it looks like. This is okay. Let's look at this part over here, the line 4 and 5. This is basically where I dump all the data set from the question, and then for this part, this is where I chose the suitable data set for our kind of simulation, the line 12 entity. Note that. Why I chose these points of data? Well, since the question asks for the 10th hour falls right in between of this kind of interval. So that's why I chose it. Okay, so and then for this part over here, this is the where we input which hour we want to find the temperature. So in the simulation, we're gonna put down 10, which corresponds to this line of command. Okay, we can skip this, and this part is just data storage for intermediate operation. When you calculate the polynomial, the Li, yeah, this kind of that value, yeah, we store it into matrix so we can see it in later time. Okay, let's look at this loop. This is the implementation of Neville's algorithm. You see, compare between these two, they look pretty much the same. Well, a little bit different, of course, since this is a proper programming. And this part over here, this is where we do the summation. Well, in case you forgot, this part, the general form is represented by this line of command, the 50th line. But instead of summing everything up all in once, we sum it one by one. Okay, we can skip this. This is just basically displaying the values of those intermediate operations. And this is where we get, this is where the values or the final answer being shown. All right, so how does it look like in Matlab command console? This is how it looks like. As you can see, it shows data set chosen, and then this is where we put it. We put the value of time, which we want to find the temperature. And this is the final answer. This is just the polynomials, the Li, calculated Li, and calculated summation step by step. Okay. Let's talk about comparisons. What are the advantages? Well, for this simulation, it's quite simple. Since it's quite simple, then hence it's suitable. Since what I meant with simple is that we are only required to use 4 points of data, and due to the small size, it is very suitable for Lagrange interpolation technique. And if you have another parameters like humidity or precipitation, you can use this kind of interpolation as well, and it skips the tedious part as too, because you don't have to recalculate this value over here. You don't have to recalculate this value all over again. if the given data is presented in the same manner, which what I meant with same manner is that those values are at the same data points, or in case it's time, at the same time, and also at the same step size. So, but what are the disadvantages of this interpolation? Well, okay, for this project, we are dealing with very small data set. Hence, it's less accurate since lesser data points. And it's also hard. And to be honest, if you want to simulate larger value of data, well, maybe you have hundreds of data points, or thousands, millions perhaps. Well, it would be hard to simulate. Why? Because it requires enormous computation power. Always remember about one thing. For every changes in amount of data points, you will have to recalculate this. And if you have hundreds, you will have to multiply by 100 terms, which is a lot. And then this modeling also excludes other factors as well, such as fluid dynamics. And to be honest, atmospheric fluid dynamics, which can be better represented by another form of differential equation. Another form of formula, which is Navier-Stokes equation for compressible fluids. Okay, aside from that, as you can see from this illustration over here, well, this is not exactly the based on the problem we have, but this is a very good intuitive insight on what are the problems faced by Lagrange interpolation. As you can see, if the time step is too big, the data fluctuation will be very big as well, and hence it will affect the accuracy of our data. So it might be not accurate in between these points. But if we want to simulate better reading, then we have to have a smaller step size. But then again, you will have to use a lot more computation power for that. And that brings us to the previous point of flaw. So I believe that Newton's divided difference is way better if we want to add more data points from time to time, since it is a better option for incremental change. And that's all for my part. Thank you.